Hey guys, welcome to this little talk on diffusion. Diffusion in the lungs happens at the blood-gas barrier, which occurs between the alveolus and the pulmonary capillaries. On the left side, we've got the pulmonary artery bringing in deoxygenated blood. And on the other side, we have the pulmonary arteries taking away oxygenated blood. In the middle is where we have the diffusion occur through the 1-cell thick epithelium of the alveolus and the 1-cell thick epithelium of the blood vessel of the capillary. We will have oxygen diffusing from the alveolus to the capillary, and we have carbon dioxide diffusing from the capillary to the alveolus. Now I'm going to introduce you to a very important law. That is Fick's law. This law describes the rate of transfer of a gas through a sheet of tissue. Here we have the rate of transfer, and this is proportional to the area available for transfer, inversely proportional to the thickness of the tissue, proportional to the gas tension difference, and proportional to the diffusion constant. Let's have a look at this in graphic format. Here is our 2-cell thick blood-gas barrier. This is the area available for transfer. This is the thickness, partial pressure of gas on one side, and the partial pressure of gas on the other side. So Fick's law is describing the rate of transfer for, say, the oxygen moving in and the rate of the carbon dioxide moving out. But what about the D? Well, the D is the diffusion constant, and it is inversely proportional to the root of the molecular weight of the gas molecule. In other words, lighter gas molecules diffuse faster than heavier gas molecules. And the solubility coefficient, which is how soluble the gas is in water. Now let's go back to our original diagram. We talked about how the deoxygenated red blood cells come in and leave as oxygenated red blood cells. Well, the red blood cells, to cross this blood-gas barrier, normally takes 0.75 seconds. This time is significantly decreased by exercise, because with exercise we have a significant increase in cardiac output. So although we have collateral circulation, the velocity of the red blood cell molecule significantly increases. So this 0.75 seconds is decreased to 0.25 seconds with exercise. Let's have a look at what happens to the partial pressure of oxygen in the capillaries as it crosses the pulmonary capillaries. We can do this in graph form. On the y-axis, we have the partial pressure of the gas, and on the x-axis, we have the time in capillary in seconds. We know that it takes 0.75 seconds for a red blood cell to blood-gas barrier, and with exercise we know that this time is reduced to 0.25 seconds. So those are the important points on our x-axis. The important point on the y-axis is the partial pressure of that gas in the alveolus. The partial pressure of oxygen will look something like this. The pulmonary veins will bring in deoxygenated blood with a partial pressure of oxygen of somewhere around 40 millimeters of mercury, and we will find that the partial pressure of oxygen increases to that of the alveolar pressure in about 0.25 seconds. Let's contrast this with carbon monoxide. The difference of carbon monoxide to oxygen is that hemoglobin has a much higher affinity for carbon monoxide than oxygen. So say we take an inspiration of carbon monoxide. the carbon monoxide will initially go into the alveolus, then it will move rapidly across that extremely thin blood-gas barrier from the alveolar gas into the bloodstream. Now, because the hemoglobin has a high affinity for carbon monoxide, so the hemoglobin will form bonds with the carbon monoxide, so there is hardly any change in the partial pressure of carbon monoxide in blood. Because no appreciable back pressure develops, the gas will continue to move rapidly across the alveolar wall. Therefore, it's clear that the diffusion rate for carbon monoxide is dependent on the diffusion properties of the blood-gas barrier and not by the amount of blood available. Thus, we call the transfer of carbon monoxide to be diffusion limited. Let's contrast this again with nitrous oxide. Now, hemoglobin does not bind to nitrous oxide at all. Thus, as a result, the partial pressure of nitrous oxide rises rapidly and virtually reaches the alveolar pressure about 1/10 the time it takes for the red blood cells to cross the blood-gas barrier. Thus, we can say for nitrous oxide that the amount of this gas taken up by the blood depends entirely on the amount of available blood flow and not at all on the diffusion properties of the blood-gas barrier. Therefore, we say nitrous oxide is perfusion limited. So what about oxygen? Is oxygen perfusion limited or diffusion limited? Under typical conditions, the capillary partial pressure of oxygen virtually reaches the alveolar partial pressure of oxygen at about 1/3 of the way along the capillary, so we can say that it is perfusion limited. However, in some abnormal circumstances, when the diffusion properties of the lung are impaired, for example cystic fibrosis, when there's a thickening of the blood-gas barrier, the blood partial pressure of oxygen doesn't reach that of the partial pressure in the alveolus by the end of the capillary, so we can say that there is some diffusion limitation as well. Our knowledge of carbon monoxide being diffusion limited and Fick's law can be combined to understand diffusion capacity. This is the rate of gas transfer divided by the partial pressure difference for the gas. Now let's go back to Fick's law, where the rate of transfer of the gas is the area times the diffusion constant divided by the thickness of the tissue times the partial pressure difference of the gas. Because in real life we can't actually measure the thickness or the area of the blood-gas barrier of the lung, we group this into one number, the diffusion capacity of the lung. Now let's consider this for carbon monoxide. We know for carbon monoxide that the partial pressure in the capillaries is generally small and can be neglected, which brings our formula something like this.